Hello, everyone. Thank you for joining us today for the Bicentennial Alliance Lecture Series. My name is Melanie Keeney, and I am the Director of Engagement and Outreach for Missouri-S&T. Today, I will serve as your host and moderator. Missouri-S&T is currently celebrating its 150th anniversary, coinciding with the Missouri Bicentennial Celebration. As a way to honor Missouri's bicentennial, S&T is hosting a lecture series titled Honoring Our Past, Envisioning the Future, Missouri S&T's lecture series for the bicentennial. This series celebrates the rich cultural history of our region and explores social and economic growth topics related to Missourians. Today, we present the fourth in our series titled Building Microsatellites for the Future. Before we get started, I'd like to go over a couple of items. First, today's speakers welcome your questions. And if you have a question and you would like to ask it, please type that into the Q&A box. The chat function will be disabled for this webinar. Questions will be asked in the order in which they are received. And those of you that are participating today in our webinar will be entered into a raffle for a participation prize. The gift bag participation prize gift bag will include Missouri's bicentennial and Missouri S&T's 150th branded items, as well as a copy of Dr. Larry Gragg's book, Forged in Gold. The winner of this drawing will be notified via email. So we'll announce that winner at the end of this webinar. And then if you could just type your email address into the Q&A box, I'll be able to get that. So with that, I would like to go ahead and introduce our speaker. Today's speaker is Dr. Pernicka, who has been an aerospace engineering faculty member at Missouri S&T since 2001. His general areas of expertise are spacecraft orbits and small spacecraft known as small sats. He is currently leading the Missouri S&T satellite research team, who placed first in the Air Force Nanosatellite 8 competition, with a pair of satellites currently under development in his lab. Students in his lab are also developing other small satellites, one of which is scheduled for launch in October of 2022 by NASA on a SpaceX Falcon 9 launch vehicle. Dr. Pernicka's degrees are all from Purdue University, and prior to coming to Missouri S&T, he was an aerospace engineering faculty member at San Jose State University in California. He is married with 2 daughters, and in his free time, he tries to keep up with his old Corvette. He tries to keep his old Corvette running and rides his bicycle over 4,000 miles a year up the many steep hills here in Rolla. So with that, Dr. Pernicka, I turn this over to you.
Thank you, Melanie. Good afternoon, everybody. I'm pulling my slides up here. It's a pleasure to be here this afternoon to talk to you all about some of the work that I have going on in my lab here on campus, where we are hopefully building microsats for the future. So today I'll start off with an overview of some of the topics that I'll be talking about. So first I'll talk about what microsats actually are and what all the excitement is about them. I'll discuss what they can do, but also what they can't do. Then I'll talk about what we're doing here on campus with our satellite research team and trying to build some of these microsatellites. I'll also talk about some of our future projects that we're working on, things here that we've been successful with and some of the challenges that we have. And then I'll end with what we've learned through all this and why we think this is something that we should keep doing. Give me a second here. I'm going to get my laser pointer going. Go to my next slide. So what is a microsatellite? Basically, it's just a small satellite. And most folks categorize those as satellites that are less than about 100 kilograms in mass, which is about 220 pounds to give you a rough idea of what we're talking about here. These are also known as small sats, and that's what most people just refer to them casually as, are just small sats. There are different classifications within the microsat or small sat nomenclature. So for example, ones that are less than 10 kilograms are called a nanosat, less than a kilogram, a picosat. And there are even a few out there that are less than about 10 grams. Those are femtosats. A very popular class that emerged in the last 20 years are those known as CubeSats. So my diagram down here shows how CubeSats are defined, and they start here on the left with what's called a 1U unit or a 1U cube. These cubes are 10 centimeters by 10 centimeters by 10 centimeters, and you can build a small spacecraft within that 1 unit of space and volume. But commonly we combine these units, we stack them, piece them together to make slightly larger small satellites that are then referred to as CubeSats. The two most common are these two right here, the 3U and the 6U. So these are sort of, building blocks that we put these satellites together. Occasionally you'll even see a 27U CubeSat out there that get launched. And so these different categories here are referred to as form factors. So you'll have a 3U form factor or a 12U form factor. And so what does the insides of one of these things look like? So this slide shows an anatomy of a sample CubeSat. So this is our M-cubed CubeSat here that we're working on campus. I'll give a few more details on it in a few slides later on. Basically, this is a 3U. So there's like a U here, a 1U, a 1U, and a 1U stacked together to make this 3U spacecraft. It's made of aluminum. The outside structure is made of aluminum. Most of the components are also aluminum, but we form this 3U aluminum structure, and then we start putting components inside of that. So here on the left end, we have a thruster. So for this mission, our mission, that's the payload. That's the component that we're trying to test on orbit. This thruster is fed from here with a propellant tank. So this tank holds our propellant, and then down below here, it's a little difficult to see, but we have plumbing. That's our feed system, and it sends the propellant into the thruster to create the thrust. On the right-hand end of the spacecraft, we have a computer that runs the spacecraft, batteries here that power the spacecraft. There are actually 4 cells in this particular CubeSat. And at the very end here, we have a radio and an antenna to send data back down to Earth so that we can see what the results of our experiment are. There are a few components, other components here that I haven't been able to list. And each CubeSat is a little bit different. You'll have different components, but this gives you a rough idea of how one of these things is put together. So what's all the hullabaloo about small sats? Well, it turns out that going to space is really difficult. To start with, we have gravity to fight, and we have a thick atmosphere to fight. So for example, atmosphere to fight. So, you might think of, well, pushing your way through the air isn't all that difficult, but it really is. If you're in a car and you roll your window down at 70 miles an hour and stick your hand out, you'll feel a pretty good push from the wind. So when we put something into orbit, the rocket has to fight its way through that thick atmosphere. And a rocket doesn't go 70 miles an hour. A rocket goes about Mach 20, which is 20 times faster than the speed of sound, which is really fast. It's even faster than I drive my Corvette. So that makes it difficult. And then gravity, my bullet here on all of, it's all about mass, right? This past summer, this picture here on the top right of my slide was my daughter and me. We went backpacking in some mountains in New Mexico, and going up and down mountains with a 40-pound pack on your back really brings home how strong gravity is. So rockets have a really hard time getting into space, and it's tricky to design them to do so. And so that makes it all about size and shape for both the rocket itself and for the spacecraft that you're going to put on top of that rocket. And so rockets are skinny so that it's easier for them to slip through the air and minimize drag. And so your spacecraft have to be small and skinny, and their shapes and masses are very constrained, whether it's a large satellite or whether it's a small sat. And it's really risky. There's no AAA in space. So if your spacecraft breaks on orbit, you're pretty much done. The mission is over. Or if it's a minor break, then your mission gets compromised at least. And because of all that, it's really expensive. So building a rocket that can get into orbit is expensive. And then if something fails in orbit, there are no do-overs. So if your spacecraft doesn't work when it gets to orbit, you've just wasted all that money, and it's really expensive to do it again, if you're even allowed to do it again. So going to space is really difficult. But in the 1990s, a new paradigm emerged. With all that in mind, computers got a lot smaller, and they also got faster, and they also got cheaper. Three really good things. They also started consuming less power and were having more memory packed into them. So when those performance specs got better, it quickly allowed for satellites to start shrinking in size. Again, both large satellites and small satellites, but it allowed the small satellites to get really small, like the CubeSats that I'm talking about today. And it also allowed universities like Missouri-Rolla to start designing and building these. A big communication satellite is the size of 1 or 2 SUVs, to give you perspective. And you can't build one of those very easily in a campus laboratory with students, but small CubeSat-sized spacecraft that are about the size of a shoebox, we can do that, and we've started doing that. And so now these small sats are really a staple of space flight in our world today, and not just at universities, but NASA, the defense industry, and the commercial industry have all really embraced small sats and CubeSats and are flying them very frequently. And so we've taken these large, expensive, big satellites that are complicated, have all kinds of bells and whistles, and we're starting more frequently now to replace them with a number of small sats. They're cheaper. They don't last as long just by their nature, but because they're cheaper, we can fly them more frequently. And, it's not unusual to have an older, larger satellite in orbit for 20, 30 years, but then that's 20 or 30-year-old technology that's being used. With smaller sats being launched more frequently, then they're more easily upgraded with the newer state-of-the-art technologies, better cameras, sensors, computers, all the cool new stuff that comes out can be flown more frequently. And also small sats are much, much easier to launch because they're smaller, because their mass is less. We can use smaller launch vehicles, or we can pack a bunch of small sats onto one launch, lowering cost. But notice it's still not easy to launch. Launching anything into space, even a small sat, is still a very tricky proposition. So what can small sats do? Well, they can inspect other spacecraft. If you have a spacecraft and maybe it's malfunctioned or broken, you can take a small sat and it can fly nearby and image that satellite and perhaps even repair it or refuel it. So if the small sat can figure out what's going on, it can be useful to try to fix a broken satellite. But also small sats are frequently used for remote sensing purposes. That is taking pictures of the Earth, for example, a Google map type of thing, weather satellites, so inspecting, monitoring radar, cloud formations to give you your daily weather forecasts can be assisted with small satellites, and reconnaissance missions. So things like monitoring forest fires, for example, or global climate effects, or even Department of Defense, keeping track of where our adversarial bad guys might be, what they might be doing. They can be useful for those purposes. And those things can be enhanced with constellations of small sats. So you take a bunch of small sats, you spread them out around Earth orbit in a variety of orbits so that you can see many different points of the Earth, and that can facilitate communication networks, internet service, and can make remote sensing missions be more effective. So like internet service, for example, SpaceX right now has hundreds, if not thousands, of their Starlink satellites beginning to provide internet service, even to remote portions of the Earth where it wasn't possible before. And then finally on this slide, swarms are starting to become of interest to the space community, where we take a bunch of small satellites and we have a swarm of those flying around in space doing various things. So my diagram here shows an example of a swarm that might look into deep space for astronomical purposes, to study a star system, for example. So you might have a focal spacecraft, small sat here, and then you have a bunch of others out here arranged in a particular way where you can aim at a particular target in deep space and image it. But these swarms, and I'll have an example of this later, these swarms can also provide communications, but they can also do this weird word here called fractionation. So back when I was talking about replacing monolithic single big spacecraft with smaller ones, that's one of the things that this fractionation idea does. And so this slide shows that concept in detail. So in this slide, each of these boxes that I show is a single small satellite. So starting in the middle here, we would have this small satellite be the computer satellite. So each of these satellites does one thing, generally speaking. Its job has just one job only. Instead of trying to do everything that your typical spacecraft would do, we break up the functionality into these, each spacecraft in the swarm. So this guy here in the middle would be your computer spacecraft. It would have your CPU, be packed with lots of memory, and also have your flight software on board. And so it's basically the brains of the swarm. Over here then to the right, you might have a payload, like payload number 1, as I have it labeled here. That might be a telescope, and it might be pointing to a star, or it might be a camera pointing somewhere on Earth. And that would be its only job. And then you might have another spacecraft, another small sat here that has a second camera or a second telescope. And then you could have as many of these small sats as you want, or as many cameras or telescopes that your mission might need. But all they do is take pictures or image stars with their telescope. As they're getting to those images back, then they send them to another spacecraft in the swarm, nearby, tens of meters to maybe a kilometer or so away, a couple miles away. And you'd have a spacecraft that just has one big antenna, and its only job is to take those data and send them back to the Earth for the ground station at Earth to receive. And so by fractionating or separating these functions, then you can have a more reliable network. You probably have some spacecraft waiting in the wings in case one of these breaks, then you would slip in a spare to take over. And then you'd also have these 3 spacecraft over here that help maintain the swarm. So for example, you'd have a visual navigation spacecraft. Its job is to take pictures of the swarm members themselves so that we know where they are, what they're doing. So this spacecraft would have neural networks running, for example, artificial intelligence, to keep track of where everybody is. And it would work carefully with this other spacecraft here, our G, N, and C spacecraft, not guidance, navigation, and control. This spacecraft would be in charge of controlling everybody. So it would have sensors like a star tracker, GPS receiver, inertial measurement unit, and it figures out where it is in space and how it's pointed. And then after that, it figures out where everybody else is. And then once it knows where everybody else is, it tells the Brainiac computer, okay, here's where everybody is, here's what everybody's doing. And based on that, then the main computer would send commands to thrusters on board each spacecraft, or reaction wheels that help twist and turn the spacecraft, push the spacecraft around to make sure they stay in the proper swarm geometry, so they don't run into each other, and so that they can get their mission done. And then you'd have one over here, a low gain antenna spacecraft. Its job would simply be to collect commands from the ground station on Earth and to send those commands over to the main computer, again, to tell each member of the swarm what they should be doing. So we haven't really flown many missions like this yet, but this is a future concept that there's been a lot of buzz around the community to do with our small sats. So what can't a small sat do? Well, they're small, so they can't transport humans around space, but they can help with human-based missions. So For example, as we're pushing onto the moon, we're going to have a lot more astronauts, a lot more EVAs, spacewalks, extracurricular vehicle activities. Those are cool, but they can be dangerous. They're expensive. They're time consuming. So anytime you can use a small sat to do inspections for you, so an astronaut doesn't have to float around in space to do an inspection, that would be useful. Or you might have a small sat along with you, kind of like walking your dog with an assistant that might help during the spacewalk to achieve some repair, some adjustment that might be safer to let the small sat do for you. Also, because of their size, they can't carry large, heavy payloads. That's not what small sats are intended for. So sometimes you just have to have a larger spacecraft to get things done. So small sats don't replace all spacecraft, just some of them. Small sats also don't have backup systems, or not very many backup systems. Because they're so small, they can't have a redundant computer or a redundant thruster. So the space shuttle, space stations, for example, they are generally triply redundant. They have 3 of everything. So if something breaks, you have 2 backup items, but small sats don't. And so when something breaks on a small sat, then it's usually done for. It's tossed away at that point, and you just have to replace it with another satellite. Small sats also generally can't do large orbit changes because they can't fit thrusters or a lot of propellant on board. They can often do no orbit changes or just small orbit changes. So the orbit that you start off in, you're usually kind of stuck in that orbit without a lot of flexibility there. And then finally, small sats can't deploy a lot of big items, appendages like antennas or big solar panels or scientific instruments or probes. So they do deploy things, but they have to be on the small side. So that leads into challenges then with using small sats. And as you might imagine then, at the top of the list is something that the industry calls SWAP, size, weight, and power. So almost all small satellites are limited by their size and volume, also their mass and their power. Because they're small and you can't deploy big solar panels, you have to use small solar panels, which limits how much power you can generate. You can't put a lot of batteries on board because they're kind of heavy. So all those things conspire against you when you're doing small sat design. Also, as I mentioned, most small sats don't have a lot of propulsion available to them. Actually, currently, most have no propulsion systems. A few are just now starting to integrate some thrusters on board, but they're limited in how they can perform. Also, guidance, navigation, and control are all tricky for small satellites. So guidance is, what's the best orbit that we should put this small sat on, or can we get it to the best orbit? And then once we get it on that orbit, navigating on that orbit is tricky. So where is it on this orbit? How can we determine exactly how close it is to the orbit that we want it on? And if it starts to drift off course, which it always does, so when it starts to drift, how do we do a course correction, or can we do a course correction? We might do it automatically or autonomously, where the spacecraft just realizes, hey, I've drifted too far here, I need to do an engine burn. Or maybe it waits and we upload a command, a human on Earth here looks at telemetry and says, uh-oh, we're too far away, let's do an engine burn to fix things. But to do that, you have to make sure that you have enough propellant on board because propellant will be a rare commodity and can be consumed. But also what we would look at that drift. So some missions, you might be able to allow a lot of drift from your orbit. Other missions, you might need to have the spacecraft stay right on the orbit. You may not be able to tolerate any drift at all. So that just varies from mission to mission. And considering all that, it gets even worse if you look at a swarm. And these swarms, we're currently talking about 10 to 100 spacecraft per swarm. And that's really difficult to keep that swarm under control. So we joke that that's like herding cats in space. And we really can't command that from Earth very well either. If we have 100 spacecraft, you can't have 100 different ground controllers on Earth watching each spacecraft and commanding it in real time or near real time. That's just too much manpower, too much ground station hardware that would be needed. So generally, the concept is you'd have a central spacecraft in the swarm that you would talk to, and then it would distribute commands out to the other spacecraft. But that gets tricky as well to make sure that those commands are getting issued properly. And again, that you're not having spacecraft crash into each other, which of course would be bad. So that gave rise then to our motivation here. You know, can we here at Missouri S&T address some of these challenges by building small sats here on campus? So that's what gave rise then to our Missouri S&T Satellite Research Team, or MSSAT for short. We started that in 2002 with two primary goals. We wanted to be able to teach our students how to design and build microsatellites that are ready to go into space. You know, the space environment is pretty rough. It's vacuum, you get very cold, very hot. So designing vehicles to last for months or even years is tricky. But we also wanted to teach our students to do this in a way where we're developing new technologies that can help some of those challenges that I have on my previous slide. So the intent is that we want to build these satellites and actually get them into space, but just getting them flight ready does most of what we want to do, which is teaching our students how to do these things, developing these new technologies. And we also want to, as an important side activity, do K through 12 outreach to try to get young people interested in this field and attract them to campus. So our team is very eclectic. We have freshmen through PhD students, a variety of majors, and we have a number of faculty and staff also on the team that help us out. And we also have, which I'll talk about here next slide, a number of industry and government partners that work with us on a regular basis. So our first partner is the Air Force. So the Air Force about 20 years ago started a neat program called the University Nanosatellite Program. It's run out of Kirtland Air Force Base in Albuquerque, New Mexico. And they run 2-year competitions for universities. So every 2 years, they pick 10 universities competitively from a proposal process. And each university team has to design and build and test a prototype of a small satellite, as I mentioned earlier, that's worthy of spaceflight, but also has technological relevance. You know, so it's not just a beep sat, as we say. It can't just orbit Earth, you know, and just be a brick in orbit. It has to actually do something of use. And so through this competition, the Air Force picks a winner or winners in each competition round, and the high finishers are manifested for an actual launch into space. So Missouri S&T and the MSSAT team, we first competed in the Nanosat 4 competition, and then we've been in every one since then, 6, 7, 8, 9, and 10. And we just last week submitted an application, hopefully to get into the Nanosat 11 round. Back a few years, we won the Nanosat 8 competition, and we won that competition with our Mr. and Mrs. satellite that I'll talk about on the next slide, which we hope to get launched in just a couple of years here. So that's been a long work in progress for us. So this slide shows a summary of what this mission is all about. So MrSat is the Missouri-Rolla satellite. It's the bigger satellite down here. MSSAT is our Missouri-Rolla second satellite. It's the smaller one on top of MrSat here. MrSat is what we call an inspector satellite. He's a microsat. He's not a CubeSat. He's a microsat. He's about 50 kilograms or about 100 pounds. And his goal is to be an inspector satellite to cruise over to other satellites and inspect a satellite. So in this case, MSSAT will act as that satellite that he's going to inspect. So we call her a resident space object. She's uncooperative in the sense that she won't communicate with MrSat at all. So what MrSat will do is to use his stereoscopic imaging system. So if you look here on the top of MrSat, he has 2 cameras strategically located here that will emulate human vision and will image MSSAT. So over here, MSSAT will be deployed from MrSat. Once they're on orbit, she'll drift away. And as she's drifting away, MrSat will use his imagers to keep track of her, and he'll know how far away she is and in what direction she drifts. And if she gets too far, then MrSat will fire up his cold gas propulsion thrusters. They run on R134A, which is a refrigerant that you find in your car or your home air conditioning systems. And those refrigerant gas will be exhausted through nozzles. There'll be 12 thrusters spread around MrSat, and that will allow him to maneuver in space and to hopefully fly in formation with MSSAT while he continues taking images of her. Again, MSSAT won't communicate with MrSat. MrSat have to rely on his cameras to keep up with her. We'll want to know how successful he is with this process. So she'll have a GPS receiver on board, and she'll beacon her location to the Global Star Network, who will then relay it to us here on the ground. So as the experiment is going on and after the experiment is over, we'll be able to tell how well MrSat did with flying in formation. So this slide shows how that mission will proceed. Right now, we're scheduled to launch on a Falcon 9 to the International Space Station, hopefully. Once on board, astronauts will put Mr. and MSSAT onto this Cyclops robotic arm here, and then fling MrSat into an orbit slightly below the space station. MrSat will power up, and he'll probably have a little bit of tumble going on, so we'll detumble him to stabilize his orientation. Once that checks out, then he will deploy MSSAT. She'll start to drift away. When she gets to be about 10 meters away, MSSAT will then use his thrusters to try to maintain that 10-meter separation and not let MSSAT get any farther away than that. Once he does that for a few minutes, then we'll go to mission mode 2, where he'll actually orbit her and continue taking pictures of her. He'll maintain that 10-meter distance and image her. Once his propellant runs out, then he won't be able to keep up with her anymore. She'll drift away. She'll burn up in the atmosphere. While that's happening, MrSat will downlink all of his images, data, hopefully to our ground station here on campus. And then eventually, after a year or so, he'll also re-enter Earth's atmosphere and burn up, ending the mission. Okay, so, oops, sorry about that. Our second mission that we're working on right now is called the CubeSat mission. That's the one that I showed the anatomy of earlier. That's our multimode mission. That's a NASA-sponsored launch. It's scheduled to go a year from now. So we have a contracted launch. We're really excited about that. This multimode name comes from a thruster that we're flying on board. Again, this is the same picture you saw earlier. This is a multimode thruster. And what's special about this thruster is it can fire in 2 different ways, a chemical mode and an electric mode. So at the bottom of my slide here, I show these 2 modes. So first, we have this chemical mode here, where we have a propellant tank. It feeds the propellant into a combustion chamber. It heats the propellant, which then combusts and blasts out of the thruster in a gas jet, giving thrust to the spacecraft. But we also have this very same thruster, the same hardware. We can also choose to not heat it. So over here on the right side, if we don't heat the propellant, instead what we do is we apply a high voltage to the end of the emitter tube here. So the propellant will sort of drip out, and as it drips out, the electrogrid here, this high voltage, will magnetically accelerate the droplets and ions of the propellant out to the right, also imparting thrust to the spacecraft. The difference is that the chemical mode is a lot higher thrust, about 1 Newton of thrust. The electric mode is lower thrust, 1 millinewton of thrust. So you might ask, well, why would we use that lower thrust level? We use this lower thrust level because it's way more efficient. It uses a lot less propellant. So if you just want to nudge your orbit, we would use the electric mode. If you want a bigger kick to your orbit, you would use this chemical mode. And so right now, this spacecraft is in our lab undergoing what we call AIT, Assembly, Integration, and Test. So we need to get this done by about next spring, and we'll deliver it to a company called Spaceflight, who will prep it for launch to go up on a Falcon 9 rocket, again, hopefully next year. So before I run out of time, we'll talk about some future projects at Missouri S&T here that we're hoping to undertake. One is this Arachne mission. That's an Air Force mission. There's a picture, artist's conception of Arachne over here. And this is a really cool space power beaming experiment. The idea is that in the future, the Air Force wants to be able to collect solar rays, convert them into electricity to power, beam them down to Earth, to military units in the field to allow them to power their operations. It could have a civilian application as well, right, to provide power for power stations on Earth as we try to get away from carbon-based power generation. And we can also power spacecraft in space, which is what we're hoping to do. The Air Force is looking for a university to provide a 6U CubeSat, which would look something like this in my bottom picture here, basically a big shoebox-sized spacecraft. And the Air Force wants to transmit power from this Arachne spacecraft to our 6U CubeSat to see how well that power transfer can work in space. Arachne was a Greek character that was an enemy of the Greek goddess Athena. So we are proposing to call our spacecraft Cluster, which was Arachne's son. So that's where these names are coming from. A second mission that we're hoping to undertake here soon is to improve the thrusters that I mentioned with our M-Cube spacecraft. So again, this one here is a mission that we've been working on for a while. We have a thruster right here in the middle of our CubeSat. But it turns out that Earth has this weird plasma environment as the solar wind, the sun blasts the Earth. The sun's solar wind interacts with Earth's magnetic field and creates this unusual plasma environment. And past thrusters that do the electrospray thing, like I described for our 3U electric mode, those thrusters can get, the ions as they exit might interact with plasma, build up charge that could then zap the spacecraft and damage it. We want to test the theory that we don't need to worry about that actually Earth's plasma can be beneficial when we operate these thrusters and in a natural way dissipate that charge. So we're looking to fly a mission where we can test a thruster and see if we can bear out our hypothesis. And if it's true, then future spacecraft can eliminate some heavy hardware they have to put on board to prevent those discharges from happening. So if we're selected to do one or both of these missions, that would probably start in the January timeframe. So that's a future project that we're looking forward, hopefully, to starting. And then a more theoretical future missions that we're looking at has to do with something called libration points. So I'll try to quickly give you a high-level overview of how this works. So in this diagram here, we have, for example, the Earth down here and the moon up here, our spacecraft flying around the moon. And instead of just orbiting the moon, sometimes we look at this L1 point here. This is where the gravity from the Earth and the moon roughly balances out. So you can actually put a spacecraft at this point or near this point and orbit this point instead of orbiting the moon itself. That provides certain advantages. We can do the same thing back here at this L2 point. And if I go to my next slide, I can show you an application of that. So you can see orbits here around these 2 points. These are called halo orbits, and they're pretty new. They've only been around for a few decades now, compared to like Newton when he showed planetary orbits hundreds of years ago. The idea here is to provide communications to astronauts that would land on the moon. NASA is working on something called LunaNet, where they have a bunch of spacecraft orbiting the moon. Our idea is that you can reduce the number of spacecraft orbiting the moon by orbiting them in these halo orbits. And you can see how the red and the purple shading here shows if you place these spacecraft in just the right way, each one will see about half of the lunar surface. And so with just 2 spacecraft, you could conceivably cover all of the moon. And then if you used swarms of spacecraft or constellations spread out in these halo orbits, you could get even better performance with more reliability. Again, perhaps using fewer spacecraft orbiting the moon itself to provide these communications. So the challenge there is, the details of how you arrange these swarms. And so that's the nature of our theoretical work that we're working on. The diagram that I have here shows an example of just two spacecraft. So the square here in the middle represents like a leader spacecraft of the swarm. And then the green lines here show how the second leader spacecraft would orbit this leader spacecraft from different three-dimensional perspectives. So it's a pretty confusing geometry, which I don't really have the time to go into here. But the idea is that you have these orbits that you need to calculate precisely in order to make this happen. Past student of mine used to call these orbits Pringles potato chips because their geometry is so odd, but they do work. But my students and I are working on precisely calculating these orbits to show that they are a viable way of doing these communication networks. Specifically, we're using genetic algorithms and numerical iteration algorithms to do this. So that's a nutshell what we have going on here. And then to last part of my talk, I'd like to talk about a little bit about our team here. I'm going a little bit long on time, so I'll hit some high points here. So the challenge here is how do you teach students, 18 to 25-year-olds, how to design and build a spacecraft? They've never really seen this before. We're actually building hardware in our lab. So we organize similarly to how industry would. We have a team leader and a chief engineer for each of our missions. And then we have subsystem groups, for example, communications, power, guidance, navigation, control. Students join their favorite group, and start coming up to speed on how to actually design and build a spacecraft. It's challenging, so we try to get freshmen and sophomores early on to join the team and start learning. We joke that it's like drinking from the fire hose because you're learning a lot in a very short period of time while we're actually in the lab doing this. We also have senior, older students mentor new team members. We even have alums that like to come back and help our team. And we throw a laundry list at them of specific training, how to write, how to code, how to design electronics boards. Spacecraft are packed with a lot of electronics, so they have to learn to solder and manage electrostatic discharge safety protocols. And then we have a whole slew of analysis software that we throw at them: CAD, finite element analysis, all kinds of things. So they learn a lot in a very short period of time. And of course, accidentally, every now and then a student accidentally graduates. We let them graduate and they take a lot of knowledge with them. So we try to mitigate that by appointing deputies. So we have a younger student paired with an older student. So before that older student graduates, they pass on their knowledge, hopefully. And we also encourage our students to hang around for graduate school. So then they can hang on to their knowledge and help give them to the younger students as well. And then we blow off steam occasionally. So we go on trips. We try to have some fun time. So this is a picture of a ski trip after one of our conference trips where we went for an Air Force meeting. And we also back here on campus, we do intramurals occasionally as a team activity to try to keep everybody sane and not going crazy. We also have a spacecraft design class that we have sophomores take to help quickly bring them up to speed. We've also extended that class to a summer camp for high school students. So we even have high school students start learning about satellites, and then a number of those students actually return to Missouri S&T and enroll here. In both cases, these students work in small groups and they build what we call a balloon sat. So in this picture in the upper right here, you can see the small balloon sat payload that each group makes that takes pictures, takes sensor readings of pressure, temperatures. When done, then we launch them on a high altitude balloon that goes up to about 100,000 feet. The balloon bursts, the payloads come back down on a parachute. Being Missouri, of course, the parachute and the payloads usually land in a tall tree. We have various ways of recovering eventually. And then the data, we bring the boxes, payloads back to campus. The data is downloaded, processed. We get some real nice pictures. This is an actual picture we got from one of our flights. It's a pretty typical picture, but also we get some really cool videos. And so it's a good way of helping our students learn how to start building small satellites. And then many of our students are doing this as part of their senior design projects. So I have to give them a grade. So we talk a lot about how we give them a grade. And, so what's an A? So if you get 90% in most of your classes, right, you'd probably expect an A. But I talk to my students about, for example, Blue Origin and Virgin Galactic are starting to fly tourists into space. Would you climb aboard one of their spacecraft if you knew that 90% of it worked, meaning that 10% of it might not work? Probably not, right? You'd probably be a little bit nervous. So you probably need 99% to get an A. So that's the challenge of doing this. I challenge our students that we've got to get 99% of it right. And even then that 1%, might ruin our day when we actually launch. So in our senior design classes and our team in general, we try to emulate industry practices with how we run things. So we don't really run it like a class, we run it more like industry. And that brings up the challenges of actually launching these things. We have to deal with range safety folks. They won't let us get on board a rocket if we can't convince them that we're 100% safe. And these guys are very risk averse. They don't like propellant tanks. They don't like batteries. They don't like radios. Those things can all be dangerous. We can't weld stuff. We can't fly composite materials. Even things that we build in our lab, they tend to get nervous about. We have to get licensed by the FCC and NOAA. That's a lot of paperwork, which leads into my third bullet here, right? We've got to write a lot of documentation to get approved for launch. Let me tell you, engineering students generally don't like to write. They like to build stuff and design stuff. So it's a challenge to get them to write and to write well. And then finally, funding is a challenge. Spacecraft hardware is really expensive. So, if you have a GPS receiver, for example, and you hook it up, Ron, and you fry it and that magic smoke escapes, that can be a $5,000 mistake, in like 2 seconds. So we joke here, we have our bulletin board here in our lab that we call our wall of shame, where we pin up solar cells and computer boards that we fried as, a reminder to the team to be careful when we're putting these things together. Again, I'm out of time here, so I'll go quickly here. We consider K through 12 outreach important. So we have a full outreach program that we require our students to do. So every semester we do a number of outreach activities, both on and off campus. And then lastly, my last slide, final thoughts. Building a satellite is fun, but it's not for the faint of heart. From experience, it's pretty easy to get that first 95% done. The design, analysis part, building the basics is easy, but that last 5%, to get it 100% ready for launch, that's really difficult. Getting that computer code to run without bugs, propellant feed lines to not leak, that last little bit is really difficult. And also this last bullet here, with the turnover, we get new students every year, and they all have really good imaginative ways that we can improve our spacecraft that's about ready to launch. But if you make one little change, there's a domino effect and it affects everything else on the spacecraft. So we usually have to say no and say, that's a great idea, but let's put it into our next mission, not the current mission. So with that, I'll turn it over for any questions that there might be. Of course, being a research team, we have required team polos, and this is Rosie modeling one of our polos, and this is Sam over here, one of our students, working on some wiring for our spacecraft. So with that, Melanie, I'll turn it back over to you. I'll be happy to take any questions that you might have.
Thank you, Dr. Pernicka, for that wonderful presentation on microsatellites. We do have a couple questions that I would like to ask of you. The first is more of just a congrats. We had an attendee that wanted me to make sure and congratulate you on your recent naming of a curator's distinguished teaching professor. For those of you tuning in that may not know, this is a great honor to be bestowed upon a professor. So congratulations.
Thank you very much. It was an honor.
So our first question I'd like to put out there to you is, given the impressive competition from other highly regarded universities, why do you think your microsat teams have had so much success?
Ooh, that's a difficult question. Well, the short answer is we have really good students, I think. But then, of course, Missouri S&T is known for its experiential learning. Yeah, it's just a lot of good hard work. We have competed against really good universities, including MIT, Colorado at Boulder, Georgia Tech. And I will tell you honestly, our students are every bit as good as them. I think we have good programs here. I personally have had a lot of really good help from fellow faculty and also a lot of staff members here on campus. I've never had reluctance from any of them to help me out in little ways and in big ways. So I mean, it's truly been a team effort.
Great. And I echo, we do have fantastic students here on our campus. Our next question is, because of their small size, do these microsatellites burn up completely on Earth re-entry?
Yes, and NASA makes us go through an enormously meticulous analysis to show that every part will burn up. We can't launch if we cannot show that. They get, in our case, they get most nervous about our stainless steel components. Most of our satellite is aluminum or other materials that will easily burn up, but aluminum, stainless steel is the one that NASA gets the most nervous about. So we go through a very detailed analysis to show that the stainless steel is not so massive that it will burn up. We don't, other materials, like more exotic materials, tend to survive reentry. We don't use those, like titanium, for example. We don't use titanium because it doesn't burn up quite as readily. So in our case, everything will burn up, but we do have to show that meticulously.
Very good. Following that, what is your view of SpaceX's Starlink service? Starlink brings broadband internet to all parts of the Earth, but also has a swarm of the satellites, one behind the other, that those of us who are photographers would say light pollute, and otherwise dark sky at night as they soar overhead.
Yes, honestly, I'm not sure how I feel about that because providing internet to remote regions of Earth, I think is a great thing, but we also don't want to compromise astronomers and photographers from getting great views. I know I know that SpaceX has started modifying their spacecraft to at least reduce the glare effects. I don't know how successful that endeavor will be. I hope it's successful. The regulatory space law industry is very new and not always mandatory. So, international space law is very much an undeveloped part of our business. And so I think those struggles will continue for the near future. So yeah, so I don't really have a good answer for that. It's a good question.
Our next question is, when Mr. and Mrs. Sat or the M3 are launched, are you and the S&T satellite team invited to the launch site to witness the spacecraft going into orbit? Also, would there be a satellite mission control on the S&T campus in Rolla, or would that be a SpaceX in California?
All good questions. So we would most likely be invited to the launch site. Would remain to be determined how closely we could actually get, whether we get VIP seating or not, so to speak. But yes, that brings up the tension of, if you're a student here, would you really rather go watch the launch, or would you really rather be in our ground station, actively watching data start coming back to us? And I'll just leave it up to the individual students. I'm sure we'll organize a road trip for those that want to actually go watch the launch, but we'll also have students back here monitoring our ground station. there are different ways we can get the data back. So MrSat will transmit his data directly back to our ground station. So here I'm sitting in our Toomey Hall building right now. We have an antenna on the roof that will pan across the sky and track MrSat as he flies over. So the data will come directly down. The M-Cube satellite works a little bit differently because its data gets transmitted to the Globalstar network. The Globalstar network sends it down to their ground stations, and they then put it on the internet. So we can just get it from a web browser anywhere. So it depends on the mission, so like the M-Cube people might go watch the launch, and then on their phone, they could actually be watching the data come in off of just a simple web browser. So yeah, there are different ways we could do that.
I think we have time for one more question. So where is the mining for the core material for these satellites being done, on Earth or in space?
I missed the first part of that, Melanie. Where's the mining being
Yeah,
done?
where is the mining for the core material for these satellites being done?
Yeah, so these are all built here on the Earth. So, the aluminum is purchased here and is formed here in our machine shop or elsewhere on Earth. Yeah, so we're not doing any kind of space mining with these missions.
Great, thank you for that. We had really great questions today, and I really appreciate everyone tuning in and asking those questions. And thank you, Dr. Pernicka, for giving your time today to participate in our bicentennial lecture series. We did have a winner for our drawing today for our gift bag, and that winner was John Gionet. I apologize if I did not pronounce your name correctly, but if you are still on, John, if you could put your email address into the Q&A box, I'll make sure and connect with you to get you that gift prize. And with that, I would like to again thank everyone for joining us today. If you would like to view this talk at a later time or be able to share it with others, it will be available in a couple days on our 150 celebration page, which is 150.mst.edu. And I'd also like to invite you for our next series lecture, which will occur on Tuesday, October 19th, here again at this Zoom link that you could find on our 150 site. And our speaker will be Dr. Petra DeWitt, who is a professor in our History and Political Science department here at S&T, and she will be talking about Missouri's German heritage. So thank you again for joining us. We appreciate you being here and hope to see you next time.